Hi, I'm Ben-Yaakov. This presentation is entitled Design Example of a Single Fault Safe Solenoid Driver. So here is the problem we are addressing in this presentation. We have a unit which is a solenoid that has to be turned on and off. This is like a coil, a relay, and there is a switch associated with it, which is turning it on and off, which is operated by a microprocessor, MCU, gives a low voltage signal to turn on the switch. So the requirements are that this will be a solid state driver like a MOSFET or IGBT or any other relevant switch. And then it has to be a single fault safe, meaning that the solenoid should not latch if one power switch is shorted or open. Well, since there is a requirement of a single fault safe, meaning that one switch will not do the job, because if there is a one switch and there is a short, then it will be turning on the solenoid permanently. So you obviously would need two switches, and the requirement is that if one switch is either open or shorted, then the system will not latch, that is, the solenoid will not be activated. This is for safety reason, because this particular application is very sensitive, and the solenoid should not be operated unless there is a need for that. And then the solenoid itself is this should be a inductor 1.2 millihenry and a resistance of 250 ohm. And this is fed by a 50 volt. So the current, the steady state DC current is 200 milliamp, but there is a requirement that the system will be operational up to a maximum of 1 amp, so that you can use a 1 amp load here rather than this particular one. Now the conventional driver will look something like that. We have the MCU. This will be a 0 to 5 volt, say, and this will be a MOSFET with so-called logic level drive. That is, it will be of a low threshold voltage, so that 5 volt will turn it on and it'll be already with a low RDS on. And here we have the solenoid. Now obviously this does not comply with the requirement, because if there is a short here, then the solenoid will be turned on continuously. So we do need two switches, and here is the possibility of using two switches in series. Now there are here gate resistors, and this MCU with 0 to 5 voltage will operate one and then the other one, so that they'll be in series. And the idea is that if one is shorted, then we still have the other one. But there are some intricate relationship here, and one has to very carefully see if under all conditions this system will be safe and operate properly. So first of all, let's start with the fact that there is a leakage through the MOSFET while the MOSFET is in the off position. This is like the output resistance when the MOSFET is off, and this is the leakage. So the voltage here is certainly not zero, and then it can float somewhere in between 0 and, in this case, 50 volt. Now, if the voltage here is, say, 25 volt, and this will be the case of when it is balanced, then we have 25 volt here. We have 0 volt here, say when the signal here is 0, then we have 25 between gate and source. So this is really dangerous, because MOSFETs are usually specified to a maximum of, say, 20 volt. Anyhow, this could actually go to even 50 volt. So in any event, this is really dangerous, so as there could be a breakdown between gate and source. So in order to remedy this, we can add a Zener diode. Well, actually there are two purposes for this Zener. First of all, it would be, of course, like higher than 5 volts, say 12 volt, and this will protect the gate against some spike spurious signals. And also in this direction, it is a diode. So therefore, when you have a current going this way, then the voltage is low, like a voltage drop on a diode. So there's no problem here of a breakdown or anything else. So that this is a nice protection for the gate to source terminal. Okay, so this will be one addition, and I'm going to put here also a Zener diode for protection against some spikes that could be coupled from other systems. So now let's have a look what happens if, say, one transistor is open, and I'm talking about, first of all, about this lower transistor. So suppose it's completely open. Well, in this case, we have this transistor connected here to the MCU. It is in the off position. There's no way that it'll turn on. And what is actually holding the voltage is to the gate to drain junction. And so therefore, this situation is safe, although it's not operational, but that's not the requirement. The requirement is that if something happens, the solenoid will not be activated. So this is okay. Now, what happens if this lower transistor is shorted between the drain and the gate? Well, in this case, we have a current going this way. This is going to be the leakage current, which is like few microamp. It's going here into the MCU, which is okay. So there's no danger here, even if there is a short between the drain and gate. Now, what about a complete short? Let's suppose the whole thing is shorted out. That's fine. Again, the current is low because this is in the off position. When it is in the on position, and if there is really a short here, then this will operate normally. So the system is actually protected against the single fault. Now, what about the upper transistor? Suppose we have a breakdown between the drain and gate, so we have a current going this direction. Well, this is really dangerous because the current here could be high. That's a low resistance and 50 volt. So this might destroy the MCU, the microprocessor. So this is something we have to protect against. And the same thing goes if there is a short here between drain and source, and you have now a path like this, and again, this will harm the MCU. So in order to remedy this, we can put a diode, which is blocking current in this direction. For operating the MOSFET, it's okay. So we are safe here. So this is a simple solution for this problem. So let's have a look now at some simulation of this circuit. And let me just point out to the extra or other element that I've added and the reason for the values that I've chosen. Okay. So aside from what we've already seen, I've added a resistor here, and here I chose the value of these two gate resistors. Now, the reason for having a resistor at the gate is because you should never leave a gate open due to two reasons. One reason is that interference and coupling of signal, stray signal, might operate the gate if it is open because the impedance is very high. And another reason is that leakage actually can turn the transistor on. So in case this is open, and I'm just worrying about the case that this line is not connected, in any event, to protect against this situation of a floating gate, I'm putting here two resistors. Now I've chosen two values. Here, the impedance when the thing is operating is 10 kilo ohm, okay? So it's okay, although it's a rather slow operation because the gate current is fairly low, but it's okay for this application. Now, here I've chosen 22 kilo ohm, and the reason is that while here we have a 10K for discharge, here the discharge will be of the gate charge will be through this resistor. Now, if this resistor is large, then it'll take a long time. And this is just a compromise that I've decided on to have this 22K with 1K here. Remember that we have here actually a voltage divider. So if you have here 5 volt, there's a drop on the diode, there is a divider here, so you cannot have this resistor R4 too large because you lose the voltage here at the gate, okay? Here it's okay because we have a 100K and actually there is no diode here. So this is the reason for the selection of these components. I've chosen this transistor, I'll talk about it in a minute. And then I have here two sources, one pulsating the battery, and this can be used in order to test for possible spikes that you might have while turning on the battery through parasitic capacitances. So this is an option here. And the main drive, which is sort of mimicking the microprocessor, the MCU, is this voltage source, the pulse voltage source, 0 to 5 volt, and I'm running it at a rather high rate, 10 millisecond on time, 20 millisecond duration, which is kind of high for a solenoid, but again, I like to see the effect of spikes and power, so I'm using this scheme. Now, this is here the window for the inductor, 1.24 millihenry, and 250 ohm is the resistance of this inductor, which represents the solenoid. Now, before going into the simulation result, let me point out to one more issue here, and this is this diode that is normally put across a relay or solenoid or any coil. And the reason for that is to capture the voltage that might generate here. So the current, when these transistors are turned off, the current will be passing through the diode rather than causing a high voltage spike that actually could harm the transistor. But today, MOSFETs are made in such a way that they can absorb some energy. This is the so-called avalanche energy absorption or capability, so that in fact you really do not need the diode. That is, a modern MOSFET actually behaves like this, as if there is a zener here, which is the maximum voltage or slightly above it. So when the voltage tends to go above it, this is clamping it, and it can absorb some energy. How much energy? It's given in the datasheet, and we'll look at it. And as we'll see, in this particular application, the transistors themselves can actually absorb the energy, and there's no need for an extra diode. So here is the transistor, and I've chosen this one, which is about 0.1 ohm resistance, and this is this package. And let's have a look now. Here is the single pulse avalanche energy, okay? And it is 32 millijoules, so it is quite a bit, and as we'll see, our design is really much below that. And then there is information about the thermal resistance in units of degrees centigrade per watt. This is a very important information, of course, to evaluate the temperature rise of the junction. Now, onsemi, this company, is very good in that it provides nice information, very useful, that many other manufacturers don't provide it, and that is, what is the thermal resistance under various conditions, okay? Normally, the value that you'll get, like thermal resistance junction to ambient, is like, in this case, 53 degrees centigrade per watt, is normally given for a 1-inch square copper layer, upper layer of a PCB, in which this unit is sitting here in the middle. So this value, 53, is for this situation. Well, this is not really very useful because we just don't have that much space on a PCB to live around this unit. I mean, it doesn't make sense. What is more realistic is something of this nature. This is the thermal pad here, the thermal pad, and well, this will be the trace. So we're interested in the thermal resistance of this situation. And here it says that it is 125 degrees centigrade per watt, which is, again, very important information. Okay, so we can use this to evaluate the temperature rise of the junction. So here is the simulation. What we see here is, first of all, the drive. This is the 5-volt from the source, like mimicking the MCU. This is the current. The green is 200 milliamp, as we'd expect. Here we see the drain voltage. This is the total drains. Here it is. This is the total drains here. And we see here the spikes due to the fact that you are turning off this inductor. So therefore there is a high voltage generated, but it is clamped. Now the two transistors are actually 200 volts together. And here it goes only to 110. And the reason is that they are probably not balanced. And also the energy is probably fairly low. So it really doesn't have to go to that high voltage. So these are the spikes which are not dangerous. Nothing will happen to the transistor if we are not exceeding the energy or the avalanche energy allowed. And we'll see that in a minute. And then I've put here the product of the drain times the inductor current, which is the transistor current. And here are the spikes during this jump. And this will be during normal conduction, which is very low. Now, in order to get an idea of the power dissipation of the transistors, I ran it at 1 second here. And using the LT-SPICE capability, I see that the average power is 6 milliwatt of the total of the two transistors. This is very, very low, of course, so we don't have any problem with that. Now, as far as this avalanche, we see here that as the current goes down, the voltage goes up. This is a zoom on the previous picture. And what we see here, that the maximum power goes to about 8, say, watts. The duration here is about 9 microseconds. And assuming this is like a triangle, then the area is the energy, and the area is the height times the base times 1/2. We get 36 microjoule, which is, of course, very low as compared to the 35 millijoule. Okay, we are 3 orders of magnitude lower than that. So there is no problem in that. So what about the temperature rise? Here we have 125 degrees centigrade per watt for this practical case. And if it is 6 milliwatt, then we are talking about a delta of 0.75 degrees centigrade, which is, of course, very, very low. However, remember that we said that we would like to have this same unit driving a 1 amp load. And if it is a 1 amp load with a duty cycle of 0.5, we get, again, the power now is 138, and we get that the 125 is again the thermal resistance. We get 17.5 degrees centigrade, and this is for 0.5 duty cycle. If, of course, it will be continuous, then it might be higher, although here we have, if it's continuous, we don't have the spikes of the turn off. So it seems that this design, first of all, complies with the requirement of the redundancy and the single fault safe, and also a term of the thermal behavior seems to be okay. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.